So, welcome everybody for coming. This is Modernizing Medicine. I think you all figured that out. South Florida Mobile Developers Meetup. We're going to go through this intro to machine learning, plus a little bit of ML for mobile. First thing I want to go through is who I am. So my name's Aaron. I work for Modernizing Medicine, full disclosure. I am a data scientist here. I've been here for 5.5 years now. I actually started as an intern and kind of have been made to a full-time data scientist. I finished my PhD in computer science, which was focused on machine learning, data science, in August. So that's why I'm here. I am dabbling now in iOS, not just because of this talk, but I was actually trying to play with it just for myself, just to learn some things. So I've started a little bit with like a Udemy course. It was like $10 over Black Friday. So I'm trying to dive into it. I didn't have the time to spend, I wasn't able to spend as much time learning as I wanted to, but we'll dive into a little bit of some of the core ML stuff and a little bit of ML for mobile. But it's really going to be a machine learning focused talk and more of an intro to machine learning talk. So just before I start that, who here actually would consider themselves actually experienced in machine learning? You know a little bit of the theory and have used machine learning models before? Okay, cool, cool. How many people have actually used it in production in some sort of production environment? Okay, good. Okay, so we have some things to learn. That's good. I'm not going to focus too much on the real deep mathematical theory, and I'll explain why later. So hopefully this has some content to cater really to everybody in the room. So first thing I want to start off with is this quote from Bill Gates. This is what I put on the meetup description, and it's really interesting because he said this in 2004. So he said, if you invent a breakthrough in artificial intelligence, so machines can learn, that is worth 10 Microsofts. If you look at where Microsoft is, they're in the Fortune top 20, 30, I think. And imagine 10 of those, right? And I think this, even since 2004, seemed almost like a prophecy. But now in 2019, almost 2020, it seems like it's actually a real thing. And maybe if you add up all of the AI and machine learning companies, it might already be close to worth a Microsoft or even more. And a big chunk of Microsoft itself now is dedicated to AI and machine learning research. So it's definitely something important. And first thing we'll start off with is kind of just what is machine learning in general. And this is supposed to this is more of an intro talk, so if anybody has any specific questions on any jargon that I use, let me know. Feel free to interrupt anytime. This can be more of a dialogue thing, because this is actually my first talk giving it to a non-data science audience. So if I accidentally say some word that it doesn't make sense to anybody here, just please let me know and I'll explain it. So the first thing is, machine learning itself, the definition of that term, is really about the field of study. And this field of study is that which enables computers to make decisions by extracting patterns from data. So this is a rough kind of workflow of how machine learning happens. You know, you start with people who are coding up systems that are collecting data. So every day you use your phone, you go on the internet, all the time data is being collected, right? And then there are the algorithms, and usually when people say the term machine learning, they're referring actually to these algorithms and the process of creating and utilizing the algorithms. And we'll go into those a little bit. But those algorithms get applied to data, which produces models. And when we say machine learning model, it's essentially a trained model that you run an algorithm over a set of data, it spits out a model. And this model now is able to make predictions for new unseen data. And I'll explain that a little bit more as we go on. But that's generally what you think about when you think about the machine learning process. But the term itself is really about the field of study. It's not really about machines learning. It's machines extracting patterns. So a lot of the hype these days you're hearing is about artificial intelligence. And so when people say machine learning, AI, they kind of conflate the two. And these days, the way people use AI really most of the time actually just means machine learning. But from a theoretical definition standpoint, artificial intelligence is this broad field of when a program can actually reason, adapt, think about like the Turing test, things like that. And machine learning is a subset of artificial intelligence. It's kind of rigid in its definition. Basically, it's exactly what I said, is you give data to an algorithm, and then it can produce predictions, and those can be more accurate over time as you give it more data. And recently, what's been really driving a lot of this AI hype, and a lot of people here may have heard of it, is deep learning models. And though deep learning gets connected to the term AI because the things that the machines can do are really, really cool and seem really difficult to actually program by hand. So it gets conflated with the term AI because it's like, this computer can detect a dog in an image, or this computer can drive a car. That sounds like artificial intelligence. But in reality, it's not. It's just responding to data, spitting out predictions, and you combine really complex versions of those models, it can create this system that looks like it's intelligent, when in reality, it's trained to do one specific thing. And I always like to say this stuff when I have any sort of venue, because as a data scientist, I get really upset when people get super fatalist about AI and saying machines are going to take over the world. My opinion is that we're not close to that at all, and we can talk about that later over some pizza. So deep learning is actually part of machine learning. It's just a subset of algorithms. It does the exact same thing as any other machine learning model, but it's just a technique for building these really complex algorithms, which we will talk about as well. So other subfields of AI that don't really fit into machine learning is the real fatalist term that people are using now is artificial general intelligence. And this is where machines can actually sense and adapt without being explicitly told, this is your data, this is your problem you're trying to solve. Even decision-based systems, so rule-based systems, technically fall into artificial intelligence because it's a system making decisions, even though a human is explicitly coding it what to do. Natural language processing is another one as part of AI. So now that we've defined what machine learning is, and I've already kind of said this, but a learned machine, essentially, right? Machine learning is the process. Now once you train the machine, you make it learn, you now have a machine learning model. And what this model can do is make a prediction. You'll hear the term inference sometimes, given a specific set of data. And I'll give you some examples. So these are all examples from my own personal data. So this is my Gmail account, right? One classic and very early application of machine learning was spam filtering. So you can take this whole big data set of a bunch of emails. You get some person to say, okay, this one's spam, this one's not spam, this one's spam, this one's not spam. Then you can take that, train an algorithm that can use the text in those images and the subjects based on who the sender is, the text in the email, and determine, okay, there's this pattern in emails that are spam, and this pattern can show emails that are not spam. You can even do a rule-based system, so if you see the word like final day sale in all caps, you could write some sort of rule at the beginning before you even get to a machine learning model that'll say, okay, just dump this into spam automatically. And I bet you in Gmail's algorithms, there's some of that stuff. But there's definitely some machine learning in there to determine between spam or not spam. So the inference there is given one of these new emails, it's giving it a label of spam or not spam, and then it routes it into your proper folder in your inbox. Something a little bit different here is recommendations. So this happens a lot in Amazon, all your social medias, all of your timelines, it's all recommendations. But I think a really cool one cool example of recommendations is through Spotify. So this is the Discover Weekly. And what this does basically is it can take all the songs that I like and I listen to, and then it takes all these other people who are users and listen to songs. It'll find the songs that are similar between us, but then maybe there's another song that somebody else listens to that I don't listen to, but all of our other songs match. It'll show that song here in the Discover Weekly, and that's a recommendation algorithm. It's a super simplified way that those recommendations happen, but that's the general idea. Another one here is Siri, right? So Siri, there's actually two levels of where kind of models come in. The first is just translating the speech to text. So the transcription takes a lot of work, a lot of machine learning. I bet you there's deep learning involved in there, and that's why it's so good at it. So there's that first level. You say something, and then it transcribes it into these words. And then the next step is how do you take those words and then make an action from it. And there's probably a mix of rule-based systems. So if you see the word remind, it'll create a reminder. But there's also probably some deep learning to determine specific context about the way that you're doing something. So in this case, I was trying to give it Vine references, but unfortunately Siri doesn't know anything about the old school Vine. So next application is photos. So this is something where we have really seen an apparent growth in the way that machine learning models can be used in everyday life was through images. Because 5 years ago, there was no way for my phone to tell me, here's all your pictures of your dog. That's actually my dog. He's cute. So Google actually went through in my Google Photos and was like, hey, there's this dog that shows up in all these photos. Do you want to give him a name? And I'm like, yeah, that's Bosco. That's my dog. And now it can just take a new image and it'll label it saying, okay, this one is your dog. And you can even search at the top there, like if I want to show somebody a picture of something, I can search, oh, this is the location that I want to look for, or this is my car, you know, stuff like that. And that's all machine learning, deep learning. There's a whole host of other applications that can be problematic or not problematic, and really now that machine learning models are starting to take hold in a lot of places in our lives, we're starting to see a lot of discussion about the ethics and use of artificial intelligence and machine learning. It's kind of outside the scope of my talk, but I wanted to at least give that introduction, because just because you can do something doesn't mean you should, and just because you train a model with, just because you train an algorithm doesn't mean it's not biased, because it's going to be biased based on the data that you give it, based on the people that code the algorithm. So these are some potentially problematic machine learning applications. Some healthcare for detecting skin cancer from images. One was recent, one that got a lot of press was the Apple Card algorithm that seemed to give larger credit limits to men than women. Predictive policing is a place that you're seeing a lot of machine learning starting to be used, and that's also very problematic. Micro-targeting of ads was a big part of the 2016 election, as well as self-driving cars. So these are all really, really great things that can help us by using machine learning models. We just have to do it responsibly. And that's all I have to say about that part. So now that we went through kind of a little bit of what is machine learning, what can it do, a big place we're going to focus on here now is how do machines actually learn. And I always like to iterate that it's really all human work that's involved here, right? So it's not a machine just automatically being able to do something. There's a lot of human work that has to go into curating data, creating the models, training them, serving them, all that stuff. So the three places we're going to focus on where this work happens is on the theory, process, and then the technology. And I'm going to breeze through really all of these things. But there's a lot of links. I'll share the slides afterwards. I'll give a PDF of the slides. I have a lot of links and a lot of resources through these parts that you can just take it. If some part interests you, you can look at it more. I steal a lot of stuff too, so I try to give all the links there. So to give kind of a concept, a little bit of a framework to how we go about training machine learning models and using them in software features, there's this paradigm, which is really cool. The article here is written by Andrej Karpathy, who is the head of AI at Tesla. And this is the software 2.0 paradigm, where if you think about regular programming, the way we write software is we put a bunch of rules together. That's really what happens. If I tap this part of the screen, make this button fire, and then do this thing. If I see kind of this phrase come in, I make it do that. And that's how we code, right? We take data and we make rules, and then we're explicitly telling through the rules how to produce the answers for whatever we're doing. Machine learning is very different. What you do there is you're not coding any rules into the algorithm. You're just telling the algorithm, here's my data, and then here's the output. You're giving it examples of what you want the machine to spit out. And the reason that this is important in machine learning, and the reason that we can't do things like object detection in images, speech recognition with traditional quote-unquote 1.0 software, is because those rules are way too complex for any human to write all of them. So what a machine learning model does is it takes vast amounts of data and it'll use mathematical algorithms to create those rules that humans still can't understand. We don't know a lot about how truly some of these deep learning algorithms work and what all the different rules within them become. We're working on that, but right now it's just a bunch of numbers flying around. But we know that it works because we can validate it on the data and those answers that we gave it. The difference now, though, is that there's a lot of work in curating that data and curating those answers. In a regular programming environment, if we see a number greater than 5, we know exactly what to do with it. But in a machine learning context, you have to give the algorithm a ton of examples of different data, of all different cases, all different types of answers, so the machine learning model can actually produce something valuable. So there actually is a lot of classical programming involved in collecting data and curating that data. But then that's where all the work becomes now. You're not building rules, you're just collecting data. And that's going to be a theme that I talk about here that's really important. So this part I'm going to breeze through, but I guess the academic part in me had to tell you about all these different types of algorithms. The main kind of machine learning algorithm you'll see is supervised learning and really classification. So what that means is you have a set of data and you know exactly what class that data belongs to. So let's say you have a bunch of images. I know this image is a dog. I know this image is a cat. I know this email is spam. I know this email is not spam. And that's the setting that most of machine learning takes place in. And those are a few different types. So classification would predict the class, spam or not spam. Regression predicts a number, so a credit limit, right? Recommendation will give you recommendations like the Spotify thing that I showed you. Unsupervised learning, semi-supervised learning, reinforcement learning are kind of more deeper machine learning techniques that deal with when you don't have labeled data. And I won't go into those specifically, but if you want to Google those terms if you're interested. Those are really, really important, especially in this software 2.0 world where it's really expensive to label data. So I'm going to focus just on a few high-level overview of a few algorithms used for classification. So think of classification as the spam, not spam, dog, cat, so on and so forth. Linear models are kind of a good tried and true method. You basically, this is, on the x-axis here is saying you have one particular feature. Let's say you have somebody's age, your y-axis would then be the credit limit. Of course, that's not going to be a great model because that doesn't have enough data, but humans can't think in more than 2 dimensions. So in reality, the algorithm is using multiple dimensions to produce that output. And then an algorithm then will be able to basically draw a dividing line, depending on whatever fancy math is inside of it, to predict yes or no on the classes. Tree models are a little bit closer to how we would think about making decisions. And what this does is it takes individual features. So rather than having a bunch of different planes now, we have a different particular features and say, okay, if I see this thing and it has this value, I'm going to follow this path. And you follow it all the way down into your specific predictions that you're making. Those are really easy to explain and say like why a model is making those decisions. And then there's of course a bunch of math that determines where you split the trees and how you do all these things. Next is some Bayesian models, which are actually, honestly, to be honest, a little fuzzy to me how they work, but I use them and they work. But they take probabilities of all your different features seen through your data, and then they spit out a probability of what your new class is going to be. So they'll say like, this email is 80% likely it's going to be spam. You set some sort of cutoff, maybe at 50% or 60%, and say anything over that percentage, I'm just going to go ahead and label as a spam. And then ensemble models, and these are the ones that really, besides deep learning models, which we're going to go into in a bit, these are the ones that are really taking over the machine learning world. And basically, it's taking an ensemble of tree models or probabilistic models and putting them all together, because then basically all these different trees can make some sort of localized decision based on this little group and pattern in the data. But if any of those things interest you, feel free to look up these terms and read more about them. So even though I got my PhD in computer science, data science, machine learning, and so forth, formulas still always scare me. That's just a thing. So when you come into machine learning and kind of dive into this stuff, this is like one really simple, relatively simple process of least squares optimization to fit a line, essentially. But there's already all these Greek letters, and I don't know what all this stuff means, and you have to figure out everything and solve all these equations and stuff. So this is usually what ends up when I look at these things. But like I said earlier, really, you can draw an analogy to things like cars these days, right? I don't know every single theory about how a combustion engine works. I don't know how rubber on tires makes it not slip when you're going up a mountain. It's the same way. I don't need to know every single mathematical formula behind how a machine learning model works for it to provide value in a business context or through a software feature. Of course, if you're doing cutting-edge research, you absolutely need to know this. And the only way that people made these advancements in these deep learning models is by knowing all of this math. And it's really important to do that if that's the setting. But these days, if you have a simple, quote-unquote simple, nothing's ever simple. It's the one thing that I've learned working in data. But if you have a kind of a business problem where it's like, okay, we have all these leads in our customer relationship management software, and we just need to prioritize them. Which ones are going to be the most attractive leads that we think we're going to sell to? That, you probably don't need to know a lot of this math. You need to know what the type of models are, you need to know how they're used, you need to know kind of what the interface will be. But at the end of the day, if you want to train a machine learning model, you just import it, and then you say, train it on this data. So 2 lines of code would actually produce a machine learning model. So what I'm trying to say is that a lot of the work actually is in collecting the data and putting all of these systems around the machine learning. Whereas these days, you can usually just import a machine learning model that'll do the actual math for you. So at least you try that first, and then if that doesn't work, then you have to go hire a PhD to figure it out. Just a brief talk about deep learning, because obviously we couldn't talk about machine learning without deep learning. But I don't have time to go into the theory of this, but if you see that, remember that formula for the linear model? Essentially what deep learning is a group of like millions of those little linear models, and they're all connected to each other. And so what that enables it to do is you're basically feeding a bunch of different connections into the algorithm, and it can basically tune all those different models in different places to optimize basically your output. So when you think about deep learning, some people have the opinion that you can throw deep learning at anything and it's going to solve all the problems in the world. I am not of that opinion, but where deep learning has really shown a lot of value is in with high-dimensional, quote-unquote, raw data. So if you think about things like images, where they have millions of inputs, right? Like even just an image that's like 512 pixels by 512, that's 512 times 512 individual inputs that you would have. There's no way a human is going to be able to determine, okay, if pixel 321 is blue, do this, and then combine all those rules to say, here's a dog. Maybe somebody could do that, but it would take them a long time to do that. So deep learning is able to work with those high-dimensional data. And that's been, again, some of the more like showy types of applications of machine learning has been through deep learning. So image detection, speech, translation, a lot of that stuff. And just here's a brief overview. So I showed an example here of the images, right? So the top right is from a data set called MNIST. It's a classic kind of handwritten digit detection data set. And the bottom one, like I still can't figure out which one's a muffin and which one's a muffin. So, I mean, somehow a machine can do it, right? And so this on the left here is just kind of a brief overview of kind of what a deep learning model looks like, but I really just don't have time to go through it. But basically, how deep learning helps is when you have no idea what to tell the computer to look for, how to create the rules, you just tell it, here's my data, here's my labels, go figure out the rules yourself. This is also just my opportunity to rant because I can. All machine learning is not deep learning. So like I said, some people think deep learning can just do anything, and they'll take deep learning, throw it at something, and all of a sudden they get a publication at a major conference now, and they didn't even try a simple model. So this is a tweet by Francois Chollet, who's actually the author of one of the most popular deep learning packages called Keras. It's a wrapper on top of TensorFlow, which just makes it a little bit easier to use and train deep learning models. And it's super popular. And if you have Twitter, and you kind of want to follow somebody who's in the AI space and really knows and actually produces some really interesting ideas, he's probably the first person I would recommend to follow. So this is one of his tweets that I screenshotted just because it was like, yeah, of course. People are like, let's throw just cool deep learning model with 1 million layers now, and it's shown that it's been state of the art in this image detection, but it was like, hey, we just have a problem where we need to know which leads are most important. You can probably sort it randomly and it would probably help them, or you can train like a very simple linear model, or k-means and logistic regression are some of the more simpler kind of classical machine learning methods. And this one's cool too. I like this tweet. I don't actually know who this guy is, but I like this tweet because in practice you find you're like, oh, okay, let's do something with AI. And so people are interested, and you're kind of like running around with a hammer trying to find a nail, right? You're like, we have AI, it's this great tool that's doing cool things, let's go use it somewhere. But first thing you have to do is determine if you even have a nail, right? And then you can use the hammer. And most of the time, it's just like a simple if statement that you can do to like feign intelligence, right? And that's enough for your users. It really just depends on the context of the business. And then, okay, maybe if you don't get everything there, you can try a machine learning model, and then it works pretty well. And then if like you really need to, after putting this in production, maybe you can try deep learning if it's like super intense. But for most business cases, you can start with simple stuff first. So that's my rant. Are we good? Any questions so far? I know I'm running like super fast, but cool. Okay, so this is going to be, so we went through the theory, right? Kind of what machine learning is, my opinions about some machine learning stuff. But here's the process about how it actually happens, and then we're going to get to technology afterwards. So when I say the process of how machine learning happens, I'm not talking about just how the algorithms are created, because those are created by like super smart math people that are like doing crazy stuff in labs. But I'm talking about how you go from nothing to a machine learning feature in some sort of product, and that could be an actual mobile app, that could be somewhere in the business. That can be any sort of like product feature. So this is the process of how do you create, how do you bring machine learning into somewhere that can produce value. And it all starts with understanding the business problem is what I'm gonna like reiterate like crazy. So this is a funny tweet. People were kind of just making Venn diagrams. For some reason, data scientists like to make Venn diagrams to describe themselves. So this one is about like all the different fields that come together to make a data scientist. And then somebody made this top part that was like, oh, haha, you know, we're just a programmer. We just copy stuff from Stack Overflow. But then somebody else was like, well, no, really, what you really need to know is what's the business problem so you know how to solve it. Maybe you don't even need a data scientist for it. So I kind of like this image and I share that a lot. So these are the kind of 4 pieces we're going to talk about when we talk about machine learning. And I didn't steal this part. This I actually made for myself. So this took a long time. So we'll start off first with the business problem, right? So this is just product management. This has nothing to do necessarily with machine learning. You have to understand what machine learning does. You have to understand your business, and you have to understand what problems you have. But besides that, it's just a regular product management pipeline. It's like, what are you even trying to do? Let's go with this example of we're trying to optimize our leads for a sales pipeline, right? We're like, okay, great. We have salespeople, and now we're not selling as much as we want to. Well, maybe you just don't have good salespeople. Maybe you got to do that. Maybe you need to hire more salespeople. Maybe you need to optimize the process. Then boom, you don't need machine learning. You're done. You saved a bunch of money. But here we have some like ROI and product market fit and problem formulation stuff. Next part, and I would say this is probably the biggest part. It depends on the application, but this is your data side. So once you know that you have a problem, you either have the data to address that with a model, or you have to even just collect some data on it. If all you have is a bunch of people's names and phone numbers for a sales pipeline, then the model's not going to help you because there's no data there. You got to go collect data. Maybe you go find information about whatever business or individual you're trying to sell to. You get some data there. Then you have to clean the data. And that's most of the work. That's most of my job, is cleaning data. And it's hard to really express how much work that is unless you work with data, because good data science kind of looks easy. It's like, oh, we made this pretty graph, we made this machine learning model, but it's actually a lot of work. You got to connect database systems. You got to make sure records are deduplicated. You got to make sure that you have all the data for those particular records and all this stuff. And then your server went down, or your VPN doesn't work, or like, you know, your code doesn't compile. Like all this stuff comes in, and that's why this is still a human problem. And then you have to kind of explore your data. Now that if you have a bunch of data, it's cleaned, you got to see like, is this even going to be possible? Like, is there even some signal in this data to produce a valid machine learning model? And then so the model building, it doesn't even start with training a model. And like I said, that training piece is really easy now. You kind of just import some library that will train the model. But you really need to design, and this kind of goes back to the business problem. You have to decide, what is your objective? Like, what is your function that you're trying to optimize? So for a sales lead pipeline, I would say, if this lead is ranked over this lead, what's the probability that I'm actually going to sell that person? So like you have to create some sort of framework for you to determine like, okay, I can make some predictions, but how do I know that these predictions are better than these predictions from this model? And how do I know that they're better than just a random guess? So you have to start off with that, creating this kind of evaluation and design framework. And then you can train models, and you can go have at it and see which ones are best and throw a bunch of code and stuff like that. And then deployment and maintenance is something that people are really still trying to figure out, because a lot of people haven't deployed machine learning model in a lot of settings. They're starting to, but these are these humongous, massive, humongous companies that can throw a lot of money at stuff. But businesses are really still just starting to put machine learning into production. So this is like, do I stand up a server? How do I keep that server on all the time? I'm a data scientist. I don't know what Kubernetes is or Docker or anything like that. What's a REST API, like that kind of stuff. And what happens a year from now when your data significantly changes and now the predictions that it's making are a lot weaker, or your population that you're looking at is just completely different. So now that you're getting predictions and you're trusting this algorithm that is probably giving you wrong stuff now, how can you actually refine that and continuously maintain that? And that's still kind of a fragmented world we're going to see when we talk about the technology. But this is really a big cycle, right? Because it's like if you get to the data part and you're like, oh, well, there's no way we're going to collect the data, then you have to go back to the business problem, on another problem. Or if you get to the model training and you find out, oh, well, we have a bunch of data and we have our problem, but none of the algorithms work. Then you're like, okay, back to the drawing board. Maybe we can, you know, descope the problem. Maybe we can make it a little bit simpler for a machine learning algorithm. And so this is a continuous process, but and there's a whole bunch of people involved from outside of just data scientists and machine learning people that are involved here. So this article actually just came out a couple of days ago, and I'm like, wow, if this came out earlier, I could have just stole this and not made my own set of slides. But this is a really good article by someone, I forget her actual title, Cassie Kozyrkov, I think is the name. She's like a head AI person at Google. And that's another person, if you want to follow on Twitter and follow her on Medium and stuff, she has some really, really nice, good ideas about machine learning, AI, and everything. And this is a good overview on that. So if there's one thing that you take away from this entire talk, is that machine learning is just about the data. If you can get good data, chances are you can build a machine learning model. If you don't have good data, you can't build a machine learning model. And then secondary to that, it is the objective you're trying to solve, right? So you can have a bunch of data, and you have to define, okay, what am I going to do? And the objective function comes in a lot when you think about the ethics questions, because if my objective is reduce recidivism rates, your algorithm is just going to optimize to whatever data is in there. And chances are, it's going to be socioeconomic status, race, zip code, that kind of stuff, which thinks the model, you think the model is unbiased, but in reality it's actually biasing towards specific data. And you need to check that kind of stuff. So it's mostly about the data and partially about your objective function. So in kind of Michael Scott fashion, I'm quoting myself, quoting somebody else. This was at a conference I went to last year, and it was a really great talk in general. I don't think it was recorded, but one of the quotes that I got was, he was saying, in the past 20 years, we've learned nothing about actual intelligence. What we have learned is how to fit bigger functions to bigger data sets. What really happened was that we were able to process more data. And that's the only reason that we were able to get to where we are with AI and machine learning. Because these algorithms existed since the 60s. And people have been dreaming about artificial intelligence since the 60s. But major advancements have gone on in other places of computer science, like database systems, mobile computing, whatever. But just in the last 5–10 years has really technology taken off as far as AI and machine learning, and that's because we're able to compute a lot more stuff. So we don't really know too much about real intelligence and making artificial intelligence. So more going to. Okay. Technology. So we went through theory, process, right? So this is the actual cool stuff, at least the stuff that I like, right? What's the tech stack actually look like? So when we think about those different processes, like I said, those different quadrants is not always code. It's not always technology there. It's a lot of people, a lot of process. But when we think about the code, there's a few different places here. So it's data collection, which is like just a regular app, right? Maybe some data scientists need to advise how you're collecting data, but to build a data collection system is you're building a website, you're building a mobile app, you're building something that's just gathering a bunch of data, shoving it into a database. That's regular software that we've been doing for years and years and years. Data processing, model building is when it kind of comes into this data science realm. Because we have to take that data that's collected, clean it, do something useful with it, analyze it, find out if it's going to be helpful, and then train some machine learning models. And that's kind of the technology that I work with on a day-to-day basis in the data processing and the model building. And then the last part is deployment. And it deals a little bit with data science, machine learning experts, but a lot of it comes back to just regular programming, right? How do we stand up a server that's going to be able to be hit millions of times a day? And how do we kind of pass data to it? How do we pass data back? How do we make those predictions? How do we, all that kind of stuff. And so that's kind of just traditional software development. So so we'll focus more on the kind of the data side of things, right? But these are really the foundational languages when you think about data science, machine learning, and code involved in those things. You're starting with data, so you're always going to have a database. And SQL is very much alive and very much a foundational part of data science. If you're dealing with not tabular data, of course, like images and speech, there's other ways to collect that data. But SQL is still very, very foundational. So this is a good slide for anybody who's looking at, kind of diving into data science and machine learning, or if you just want to be able to kind of converse a little bit more easily with a data scientist and know the tools and technologies that they're using. So besides the data side, Python and R are the main programming languages, like foundational programming languages that data scientists use to explore data, train models, and so forth. And then R itself was actually built to be a statistical data processing language, whereas Python is a object-oriented / scripting language that has a lot of data and scientific computing packages in it, and they're both very popular. There's always these wars of Python or R. I kind of don't get involved in those. You use whichever's best for your team, what people know, or for whatever you're trying to do with them. But there are some new kids on the block over here. So Julia is a kind of numerical-oriented programming language that is being built. JavaScript even has machine learning libraries, which is terrifying. And Swift, as I've been seeing a little bit in my research, right, Apple has created Swift to be a general-purpose programming language, right? They didn't want it to just be for iOS. And I've heard some people playing with it and seeing some things around like CoreML, and even just some other deep learning stuff. People starting to actually like it for some data science stuff. So, we'll stay tuned for that. We'll see how it goes. But that's really Apple's goal, right, with Swift, is to start to encompass more workflows than just mobile computing. So those top level there is all languages, but I'm going to talk about more just technologies and packages kind of within those languages. So if you think about, if we look at these, so these two guys here, Pandas and NumPy, are two Python packages that are really the foundation of data processing within Python. You really couldn't do a lot of good stuff without these two. And now people use it, researchers, general people. I use Pandas and NumPy all the time, and they're really great packages to learn. And that's actually the first thing that I learned when I went into data science, was I took a Udacity course and they gave an intro to Pandas and Python. So if you're already a programmer, that's really the way to go. I would recommend is start on the Python route, Pandas and NumPy. If you're not already a programmer, I would suggest R, because that's more just helps you think about data and statistics. But dplyr, so R itself is a bit more fragmented as far as the package ecosystem, but it was built from the foundation to be a data processing language. So Pandas actually is modeled after how R handles data. So there's that. But then this package called dplyr is one of the kind of top packages for doing similar Pandas-like stuff, basically SQL-like operations, like how can I filter data, how can I group data, how can I summarize it, join tables together, things like that. Those two packages really abstract away a lot of those actions into a nice kind of domain-specific language that you can do with. Spark there on the right is a big data processing engine, and it actually has bindings for SQL, Python, R, Scala, Java. And we use that day to day at Modernizing Medicine for all of our data processing, because we just have huge volumes of data. So if you have quote-unquote big data, large amounts of data, Spark is a good way to go. But if you have a data set that can fit on your laptop, you don't really need Spark. But that's something really important to know because it's very, very popular. Yep.
Is there anything like towards the C++ level? Because I know TensorFlow is written in like C++. What are some of the packages on that end if you're using those kind of languages?
Yeah, I don't know if specific packages. I know a lot of this stuff, like a lot of the R packages are actually written in C++ and they interface with R. Python has some. I think Python has even some like Fortran deep down in there somewhere.
Yeah, you do a lot of numerical.
Exactly, and I don't know specifically of any C++. I know people have done some things, but
Torch, right?
Torch originally was in C++, and actually there's a package, deep learning framework called PyTorch, which is a port from Torch into Python, and that gained popularity, but yeah, that's what Torch was, and that was specifically deep learning. And so I think the reason people use Python and R is not, like, C++ would be great at model training, right, because it's super fast, it can be optimized and everything. But Python and R bring the other ecosystem of just processing data, just like cleaning data, visualizing data, that maybe is lacking in C++, which you would have to jump back and forth if you were going to do that. And some people do, like if you really need that fast raw processing power.
Because I do a lot of development mobile, but I do it in like C and SDL. So I'm using the NDK, so I don't want to go up to a higher level language and come back down again.
I got you. And that might be where it's like, it's useful to have that kind of model training in that lower level language, and then maybe there's either like another team member, like person, or just working in another language just to get the data all sorted and situated. But if your data is clean, it's probably just fine to use those. I just off the top of my head don't know of any of those packages. Oh, okay, so here's PyTorch. So these three here are machine learning libraries. So scikit-learn is really like the go-to place to do machine learning in Python. and they have fantastic coverage of machine learning algorithms and fantastic documentation. So I would even suggest, if you're trying to get into this stuff, learn Pandas and NumPy first, but then even if you don't know a whole lot about machine learning theory and the algorithms, just run through the scikit-learn documentation because they cover everything really, really well. They introduce things well, and their API is very consistent, so you can just try a bunch of different models in a really consistent manner. On the right side, I actually didn't circle it, but that Tidy Models package, like I said, R was a bit more fragmented. Basically, it was somebody who created some cool algorithm and they made a package just for that one algorithm. And this other person made a package for one algorithm. So R programmers tend to have their favorite package for doing a machine learning model. So it's kind of hard to find the right ones. But this Tidy Models package basically tries to do what scikit-learn did and create a consistent interface for all those models. Whereas the people who are maintaining the individual models are actually a bunch of different people. And in the middle here are the big guys that are getting a lot of press and buzz. People are wanting to learn them because they're the deep learning frameworks. So TensorFlow, made by Google, it's a little bit older, a little bit more established. PyTorch is the Torch port, the C++ port into Python created by Facebook. And those are really the two go-to frameworks for deep learning model training. So the image stuff, speech, translation, all of that stuff. And they both have a couple wrappers that make things a little bit simpler because at the bottom, really what TensorFlow and PyTorch are just numerical libraries that are optimized for doing kind of deep learning and running on GPUs and stuff like that. Excuse me. But there's some higher level packages that maybe you don't have to interface directly with them. But those are the two to know. A lot of the embedding happens with TensorFlow because they really started off with like, we want to build machine learning and we want to be able to do machine learning like on mobile devices and on smaller compute. But PyTorch is catching up a lot, and the academic community really likes PyTorch a lot these days. So you should see that catch up a little bit more. But I'd say most of the deep learning in production that you'll see right now is in TensorFlow. So along the side of the new kid on the block is CoreML over there. And only new because I actually didn't know about it until I started doing research for this presentation. But CoreML is really cool. So it's Apple's, essentially, machine learning library. And they released it 2017, I think, and they've been really advancing it a lot. But they interface actually with things like TensorFlow, some other machine learning models. It was the first time I actually saw like a GitHub page from Apple because they were doing something, they had a package in Python to interface with TensorFlow. And so that's like a way that you can use a lot of machine learning within iOS. They even have CreateML, which is a drag and drop kind of user interface for training machine learning models. But you don't necessarily have to do the Python and R code. So that's something that I've been reading up a lot on and I've been trying to play with. I was hoping to get like a CoreML demo ready for this talk. I just didn't have time. But the bottom here is the world of model deployment. And it's kind of scarce because there's some packages here and there. There's not really any good like go-to, like if you're gonna deploy a model, use this framework. Probably eventually we're gonna get there. And I think that's the goal of that one on the right, MLflow. It's from the makers of Spark, actually. And that's supposed to be, it's an open source package. It's supposed to be a framework for basically training models, maintaining them, keeping track of, okay, this model was the best and we're gonna deploy that one. And then you can keep track of all your different train runs and everything. And so as far as deployment, right, it's just like how can you actually serve prediction somewhere. POJO there, I just typed those letters, is, if you're not familiar, stands for plain old Java object. Some machine learning libraries will actually get a trained model and then basically generate a function with a bunch of if statements inside of it. So the function has some interface, it spits out yes or no or something like that. You can just take that file literally and just dump it into your Java project. So there's concerns about maintenance and versioning and stuff like that. But if that's one of the more rudimentary ways of deploying a model. And then Docker I threw on there because I feel like you have to be cool, you have to say Docker. And so essentially, right, if you train a model, if there's data scientists over here on their laptop and they're training a model, they downloaded all these packages and who knows when those packages are from, who knows whether specific settings are on the machine. But if you can launch some instance in the cloud in a Docker image, you can just take that image and just move it over here behind some sort of serving layer and say, okay, make my predictions from there. All the versions are going to be exactly what had to be inside of that Docker image. And people are doing that a lot for some deploying machine learning models. So. Going into that a little bit more, like I talked about, inference is what we're talking about when we're talking about deploying models. We already did a whole bunch of work on collecting data, analyzing data, generating running an algorithm, generating a model. But now it's like, where do we put this model so somebody can actually use it and get information from it? Where do I put it so I can get new spam, not spam recommendations, or new dog, cat recommendations? And so the more complex your model is, the more computation it takes to make an inference or a prediction. So if your model just says, if subject in all caps, label as spam, you can embed that in any sort of thing that you want. It's just one, what is it, the notation, O of 1 computation, right? It's like, it just has to make one quick decision. But if you have a deep learning model that has 10 million parameters, that means 10 million processes that have to happen just to make one prediction. That's going to be really hard to embed in some sort of mobile environment. So when you think about the model deployment, there's really 3 options that you have. One is offline or batch model scoring. And we actually use this for some things, which is like, consider maybe like you have a pipeline, you need to augment some data. Let's say there's a particular variable that you're trying to capture, and you don't always have it captured. So maybe for some reason you don't always have the state of wherever your lead is in. But you have some other information that could help you determine what that state is. You might train a machine learning model to fill in that missing data, but then you don't need to make a prediction every second for that. You just need to run it once over your data, and then you save it, and then you save that prediction, and then you're good. So that might happen once a day, once a month, or whatever. The middle is probably the most common form when you have to make live predictions, is through some sort of server somewhere that's serving predictions. So you get some, and that can scale however you need it to, right? So you have a super complex function, you can just spin up some humongous instance that's sitting there, just serving all day long, serving predictions. So that just becomes just like a regular kind of API system. So if your system is more of a thin client kind of mobile app, then it's fine, that's already your workflow. You're always going back to the server for things anyway, so you might as well just go back to the server for your machine learning model prediction. And then the last option is an embedded model. So it's where you take that model and you actually put it on to the phone. And right, we're talking about the context of mobile computing, right? So you take that model, put it into the phone, and the data is just going back and forth here, and the computation's happening here. So I know this is the mobile developers meetup, so we're finally getting into the mobile part. So when we talk about inference is really where we're talking about mobile with regards to machine learning. We can actually talk about training too, which is really interesting. But first off with inference. So what happens when you can deploy your machine learning model onto a phone is, first of all, you are offline now. You avoid a trip to the server. So you can make a prediction even though somebody's offline. Really interesting applications in places where there's limited internet connectivity and you need to make model predictions. And also, you don't have to stand up a server. You're not paying for that server. The compute is actually happening on the user's device. So it's quote unquote free computing. It's not your computing, it's computing on somebody else's machine. So that's the kind of the pros for doing that kind of stuff, deploying your model into a mobile device. And some really interesting work recently, just in the last few years, is on actually doing the training on a mobile device. And that's a really great example of that is the Face ID. So Face ID, Apple doesn't store any of your face data when you scan your face on their servers. So they have some sort of model that's trained initially that can generically kind of separate some stuff. They take that model, send it to your phone, and then when you scan your face, it does like the final level of training of that model that can determine your face. And so then the model is trained, only lives on your phone, then your data is not anywhere. So training on a mobile device is really good for privacy concerns, as well as if a model just needs to be personalized, like super personalized to individual people, that you're never going to cover all of the cases on a server. You're never going to get all the data, but you can pre-train a model, send it to a phone, and then do the final bit. That's really useful. So some cons for machine learning on mobile, though, is you're still going to have some limited model complexity, right? A phone has a crazy amount of processing power, but not quite as much as you can get still in the cloud or on your own machine. You're also going to have to think about like just plain old battery consumption, right? You're in the setting of a mobile computing world. If you're just processing all day long to make these inferences, you're just going to wipe out your user's battery, right? So you have to think about that. As I was doing some research, and actually somebody on my team sent me an article by this team, it's I think called Fritz AI, and they're a really cool organization. So they're a company that kind of tries to help do AI and machine learning on mobile devices. So generally, somebody who's a mobile developer and who's a data scientist really live in separate worlds. And they're trying to kind of bridge the gap on those and bring the machine learning and mobile together. So this is a really great article just talking about what you can and can't do with machine learning on mobile, or what you even should do on mobile or not. Like I said, if you have a regular app that's just already going to the server all the time, you probably don't need to do your machine learning on mobile. But if you have things where you need to do like image detection or AR or that kind of stuff, that's where machine learning on mobile can really be useful. And so I would suggest reading this. It's a bit of a lengthy read, but it's really interesting, and it level sets kind of how you can use ML on mobile. So just for now, I'm going to bring back one of my favorite images. We'll just talk about, the way we're going to talk about the rest of this now, ML on mobile, is just thinking about images. That's a really, really big use case, right? You have an amazing camera right here, and you can point in at things, and you can take pictures. So let's just talk about images some more. This work here, and the reason images have even really taken off as far as AI and machine learning, we'll go through a little bit of a history lesson here, is this data set actually called ImageNet. And the work here was started around 2007. There was a researcher who basically wanted to just collect a bunch of images and have labels on them so we can kind of use it. And then they were like, at the time they really didn't know like how impactful that data set was going to be. Well, looking back, we see that it's like really one of the main things that kind of transformed AI research with images. So basically what ImageNet is this giant database. It has like 27 million images now. It started off with like 3 million, but of just a bunch of objects. So it was like, it had this hierarchical structure of like, okay, here's mammals, and then here's a dog, here's a human, and then like here's an automobile, and then there's a car, and there's a truck, and all that kind of stuff. And they just collected a ton of images. So they actually used Amazon Mechanical Turk for humans to label, because it's a really challenging problem to get labels. They labeled like a bunch of images and created this sort of like nice data set where people could start to do research on, okay, how can we train a machine to like actually classify these images properly and better than a human. So if you read this article on Quartz, they kind of go through the history of what happened, and they go through how accurate the model was. So in 2012, I believe, don't quote me on this, actually I can just click this article, because it is very interesting. Oops. Oh, those are my notes. Oh, I guess I don't have the link on there. Okay, anyway. But if you Google that article, I'll add the link later. They have some timelines of how the accuracy went. I think somewhere in 2012, the machines were getting like under 50% accuracy. And then around 2013, 2014, Google came out with this kind of deep learning neural network architecture that was able to finally get the model within like under 25% error. And then now, fast forward to today, all these deep learning models are getting less than 5% error, which is greater than a human. So this is a problem. This data set really transformed the way. What it did was it created this competition-like structure for training and creating deep learning and machine learning models that really, and was a way to benchmark and compare different models, so people were able to like make huge optimizations. And so all the optimizations in deep learning and the technologies that they built to solve this ImageNet problem have been translated to a bunch of different places, because the deep learning model the algorithm itself can be used on different types of data. So ImageNet is a big thing. And if you look at, these are the types of models, and they all have these weird names. But on the x-axis here, it's gigaops. But think about the x-axis as the amount of operations that it takes to train that model. And then the accuracy is on the y-axis. So you'll see that it's kind of like this kind of line where it takes, to get more accurate, it takes more and more operations. But the problem with this is if it takes more and more operations, you need more and more complex hardware. You can't put it on a phone. But since around 2017, and now I'm starting to steal content from one of my colleagues, I'll give him a shout out soon. Around 2017, this model called MobileNet came out. And what MobileNet did was it was able to get comparable or better accuracy than those huge, ginormous models, but they put in some optimizations to make a lot less parameters in the model. So I know I didn't explain exactly how deep learning works, but all you got to do is look at these numbers. See how the top line is 4, the bottom line is 138, which basically a parameter means a model has to make a decision. So there's 4 million decisions that had to be made on that mobile version versus 138 million decisions. So it makes it easier to actually start to, basically reduces the computation that's necessary to train and score these models. I'm not like a super expert on this stuff, so I'm learning as well as you guys. So this is the talk that I stole it from. William, one of our colleagues, he gave a talk at PyData Miami meetup a few months ago. And his talk, if you're interested, was really focused on deep learning for mobile. So he goes into a lot about, it's really all about deep learning. So if you're not in the deep learning or machine learning world, a lot of the terms might kind of be a little much, but he gives a really good talk, and he gives a lot of that history about how deep learning advanced, how deep learning for mobile started to come about. And he gives this example of an object detection app on a phone. I was actually hoping to try to build that and show you live here, but I just didn't have time. But for now, we can just watch this video. Okay, yeah. There we go.
So you can see it thinks we're maybe in a library, or
this is actually connected on his phone. You just have an app right there, and it's doing live
water bottle
object detection.
It's like, or a bake shop. It's maybe 40% sure. I wonder what it thinks this is. Dumbbell. Okay, it's actually chapstick. But yeah, so this is kind of an example of the kind of accuracy that and speed. You kind of see the latency on the bottom there. It's running pretty fast. This was about a year and a half ago.
Your screen refresh might be hurting it too.
Yeah.
It might actually be doing it faster.
And the I/O streaming video to another device. I'm not sure. But yeah, this is that's that one. And then also you can have a object detector, which can identify chairs and people, and it can move and see new things, or your
yeah, so if you can't read it, it's kind of trying bounding boxes around different things, like it's a chair, it's a person, it's a bottle, a keyboard. This is really, really cool, exciting applications of kind of machine learning on mobile devices. And this is live, real time, so it's taking these pictures, processing it through those 4 million parameters instantly, and making those predictions instantly. Even the Google Photos thing that I showed you happens on a server. It has to go through, find all of my images of my dog, well, find all of my images, and then figure out that there's this group of images that are probably of the same dog. And then it tells me, like, in a few days. It does this computation kind of offline, not exactly with me in front of it. So this deep learning stuff for mobile devices is really going to open up a whole bunch of really cool applications. And even the Udemy course that I'm taking now has some sort of app that you can build with AR to do like Pokemon Go type stuff, where you can like catch the Pokemon like real life. So like, you know, our Pokemon Go is just going to get better. So, you know. So back to this. This is my last slide, so just so you know, we're almost done. These were the two articles I was going to use to try to hopefully show you a live demo of object detection. Here, I just didn't have time to, but I have links on both of these. If you're interested, you can look it up. The one on the right here is from Apple itself, so with Core ML, ways that you can actually put object detection into any iOS app. And then the right there is using TensorFlow Lite, which is their method for deploying and embedding models inside of mobile devices, where you can, these both are doing the object detection type things, but it's really simple, like not a whole lot of code involved, especially if you don't need to train anything. What you can do a lot of the times is take a model like this and then give it your own set of images, and maybe you always need like a couple hundred images, and you can say, these are the type of images that I'm trying to look at. There was one other article that I found where he trained the model to detect different types of sushi. So you can just show it different pictures of sushi with categories, and it'll be able to do that kind of stuff. So that's it for me. You can find me anywhere with this handle: Twitter, LinkedIn, Instagram, Facebook, anything on the internet. So if you have any more questions, you can ask me there offline or ask me now. So thank you.